In this video, you'll learn how to do 3D vector operations, such as addition, subtraction, and scalar multiplication. Also, you'll learn how to find the linear combination and dot product of two vectors. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It's very important for the continuity of this channel. We begin by defining two basic vector operations, vector addition and scalar multiplication. The sum u plus v can be formed by placing the tail of the vector v, red arrow, at the head of the vector u, blue arrow, and then joining the tail of vector u to the head of the vector v gives the vector u plus v. The green arrow shows the sum u plus v. Because vectors are not affected by translation, the initial point of vector u can be moved to any convenient point by making an appropriate translation. Then this gives another way to construct the sum, which can be formed by placing the tail of the vector u at the head of the vector v. Both constructions together form a parallelogram, and we can see that the sum of these two vectors lies along the diagonal of the parallelogram, with the vector u and the vector v as sides. Definition of vector addition. If u and v are vectors positioned so the initial point of v is at the terminal point of u, then the sum u plus v is the vector from the initial point of u to the terminal point of v. And we have just seen the first property of vector addition. Vector addition follows the commutative property, which means the order of addition does not matter. Sums of vectors are easily expressed in terms of components. Vector addition can be performed simply by adding the corresponding components of the vectors. Another property of vector addition is the existence of the additive identity. The identity property of vector addition is that when a vector v is added to vector 0, the result is the vector itself. It is named the identity property because when applied to a vector, the vector keeps its identity. Now we will learn how to multiply a vector by a real number. The operation of multiplying a vector by a real number is called scalar multiplication because the term scalar is another word for real number. If lambda is a scalar and v is a vector, then the scalar multiple is the vector whose length is the modulus of lambda times the length of vector v, and whose direction is the same as vector v, if lambda is greater than 0, and is opposite to v if lambda is less than 0. Now let us understand visually the scalar multiplication of the vector. Multiplying by a scalar lambda stretches a vector out by a factor of lambda. Let us see an example. We draw vector v and take the value of lambda to be 3. If we multiply the vector v by 3, the new vector is equal to 3 times the old vector. The multiplication of the vector v by the scalar 3 doesn't change the direction of the vector, only its magnitude. In this example, the length of the new vector is equal to 3 times the original vector, and its direction is unchanged. The result of scalar multiplication is also a vector, where the magnitude of the original vector is multiplied by the value represented by the scalar. Let us see another example. We draw a vector v and take the value of lambda to be -2. If we multiply the vector v by -2, the new vector is equal to 2 times the old vector. The multiplication of the vector v by the scalar minus 2 changes the direction, since the scalar is negative. The new vector flips around by an angle of 180 degrees. In this example, the length of the new vector is equal to twice the original vector, and its direction is changed by an angle of 180 degrees. Scalar multiplication is distributive over vector addition. To multiply a vector in component form by a scalar, multiply each component by the scalar. To perform vector subtraction, we use a similar process to vector addition, but with a slight variation. We add the first vector to the negative of the second vector. To demonstrate this geometrically, let's take the vectors u and v. By placing the tail of vector v at the head of the vector u and then connecting the tail of vector u to the head of the vector v, we can visually add u and v. To perform a vector subtraction, we add vector u to the negative of vector v. Remember that the negative of a vector has the same magnitude, but the opposite direction. Thus, we begin by drawing the vector minus v. Then we add the vector u to the negative of vector v by placing the tail of vector minus v on the head of vector u and drawing a new vector from the tail of vector u to the head of vector minus v. This is one method of subtracting vectors graphically, but there is a faster way. Since the vector u minus v, when added to vector v, gives the vector u, we can think of the vector u minus v as a vector that goes from the head of vector u to the head of vector v. We can define vector subtraction as follows. For two vectors u and v, the difference u minus v is the vector from the terminal point of v to the terminal point of u. In the component form, we subtract the corresponding components in the order of vector subtraction. Now we will see how vector algebra works by solving a simple example. Given the two vectors, find. Vectors u and v are represented in terms of the standard basis vectors I, j, and k along the x, y, and z axes. To solve item A, we add the corresponding components individually. That is, we need to add the I, j, and k components separately to get the sum of these vectors. To solve item B, we subtract the corresponding components individually. That is, we need to subtract the I, j, and k components separately to get the difference between these vectors. Item C is a combination of scalar multiplication and vector subtraction. I'd rather write these vectors in component form instead of standard basis vectors. The scalars can be distributed among the components of the vectors, and then we perform the vector subtraction. I will take the two operations, scalar multiplication and vector addition, to introduce the concept of the linear combination of two vectors. Let's start by understanding what a linear combination is. In mathematics, a linear combination is an expression made up of a set of terms that are multiplied by a scalar and then added together. For example, The expression ax plus by is a linear combination of x and y, where a and b are scalars. Another example is 2x plus 3y minus 4z, which is a linear combination of x, y, and z, where 2, 3, and minus 4 are scalars. The definition of the linear combination of two vectors is given as follows. A vector w is called a linear combination of the vectors u and v if it can be expressed in the form w equals to c times vector u plus d times vector v, where c and d are scalars. In short, a linear combination of two or more vectors is the vector obtained by adding two or more vectors which are multiplied by scalars values. Let's start with an example by using vectors in two-dimensional space. Express w as a linear combination and then sketch w. We must find r and s such that r times u plus s times v equals to vector w. We now use scalar multiplication and vector addition. Equating the components of the vectors on each side of the equation, we arrive at a system of two linear equations. This means that w is a linear combination of u and v if this linear system is consistent. Adding the equations, we obtain r equals 2, and setting r equals 2 in the first equation yields s equals 4. Since this system has exactly one solution, it is a consistent system, and w can be expressed as a linear combination of vector u and vector v. We now write the vector w as a linear combination of the vectors u and v as follows. We now sketch the vectors. You now should be wondering, why is a linear combination linear? We call these operations linear because they operate on a line. When you scale a vector, the new vector is a further out version of the original on the same line. The next example is similar to the previous one, except that the vectors are in three-dimensional space. But the process is the same. You could try to solve it yourself and then check the answer.